Empezamos ahora con la segunda sesión de charlas del día de hoy, del 19º Simposio Latinoamericano de Lógica Matemática. Paso inmediatamente la palabra al profesor Max Freund, que será el moderador de las próximas dos charlas. Muchas gracias.
Good afternoon. I am honored and pleased to introduce Professor Luiz Pereira from the Catholic University of Rio. Professor Pereira will give us a talk on the anti-symbolism and its relationship to the spousal principle. After his talk, we're going to have a period for questions. Pereira, please.
As the other speakers would like to thank the organizers for the kind and generous invitation to come back to Costa Rica, to this big part of this fantastic meeting and to be in this fantastic country. In fact, when Snyder invited me, I talked with Elaine, and we thought that it would be a good idea to have a double section on communism. So we would have 2 hours of logical version. But eventually, after that, we decided that it would be more interesting to have just one session on communism, logical communism, and we'll talk about this topic today, which is related to communism. It's also related to communism, but it's a byproduct of what we have been doing. So my talk today is about it is for revisiting expulsive and disjunctive syllogism. So I will discuss some relations, some old relations and some new relations between the two very famous principles. This is a joint work with Elaine and Oyster, and this is my people Nascimento. I think I could resume the whole point of my talk with this quotation by Wittgenstein. Wittgenstein says, contradiction is to be regarded not as a catastrophe, but as a wall indicating that we can't go. And this idea of the wall, don't go, is really present in my talk. What is the problem? The disjunctive syllogism seems to be part of our not problematic or unusual inferential practices. But on the other hand, at least superficially, it doesn't seem to be related to depend on our acceptance of the frequently disputable expulsive rule. We know that the acceptance of the expulsive right is a sufficient condition for the acceptance of the disjunctive syllogism. For example, the following derivation will do the work in intuitionistic natural reduction. We assume B not B, we derive bottom, and from the bottom use the principle of exposure, we derive A, and then we assume A, and by disjunction elimination, we derive A. So, given the expulsive, we can derive the disjunctive syllogism. But the interesting question, and that's the question I'm going to talk about today, is the expulsive a necessary condition for the acceptance of the disjunctive syllogism? The aim of my talk today is to discuss some possible ways to define systems. I'll talk about 2 systems that combines the preservation of the disjunctive syllogism and the rejection of the expulsive. So I can announce already the interesting system that I'm going to present to you today is a kind of intermediate system between minimal logic and intuitionistic logic. It's really an intermediate system between minimal logic and intuitionistic logic. The expulsive and the disjunctive syllogism, their relation is an old story, as you know. For example, this is the quotation from Diogenes, from the lives and things of eminent philosophers, where Diogenes describes the Stoic, in the Stoic philosophy, the fifth, undemonstrated. And I quote, type 5 undemonstrated argument is an argument which has an explicit disjunction and a contradictory of one of the disjunctive premises infers the order disjunction. This is a very famous phrase. Either it's day or it's time, it's not night, therefore it is day. And just another nice quotation from an argument that is attributed to William of Soissons, an argument that aims to show that anything follows from an impossibility. And this is the quotation, and I quote, I wonder that a certain man proposes the thesis that from a bare set of impossibility, anything whatsoever follows. For doesn't it follow that if Socrates is a man and not a man, then Socrates is a man? But if Socrates is a man, then Socrates is a man or a stone. Therefore, if Socrates is a man and not a man, then Socrates is a man or a stone. But if Socrates is a man and Socrates is not a man, then Socrates is not a man. Therefore, if Socrates is a man and Socrates is not a man, then Socrates is a stone. First, the construction, very easy construction of this argument is this one. So this is just a repetition of what I have shown in that quotation. If Socrates is a man and not a man, then Socrates is a man, etc., etc. And the conclusion, therefore, if Socrates is a man and Socrates is not a man, then Socrates is a stone. We can also formalize it this way. Not true. It's very, very easy. And this is a natural deduction, derivation, which aims to show the same thing. We assume B, and then we have A or B, and then assume not B, and then by conjunction introduction we have A or B, and then we have the axiom or the theorem of the degenerative syllogism, and then by modus ponens we have A, and then we discharge the two hypotheses B and not B, and then we derive the axiom of the X-force. Or the theorem. The same result can be obtained if we have a kind of disjunctive syllogism rule that I call DS, and this is the rule, to minimal logic. And then we could have this very easy derivation too. We assume B, and then we have A or B, and then we use not B as an abstract assumption, and then using the new rule DS, we derive A, and then we derive not B. Implies B implies A. And it's interesting. It's interesting to observe, and this will be very important later, that this derivation is not normal. Normal in the sense of proof theory, right? We have introduced A or B, and used A or B as a major premise for the elimination rule. So there's a rule in this derivation that, in a certain sense, must be eliminated. But is this the only way we could use to justify our legitimate use of the degenerative syllogism? Is it really necessary to resort to the X-false in order to justify the degenerative syllogism? Maybe we could try to use a kind of admissibility argument that has been used, in fact, and that this admissibility argument to justify the degenerative syllogism. And this strategy, strategy like this, was mentioned by Tim van der Hoven in a very interesting paper called The Correspondence Between Johansson and Haydn. The title of the paper is The Johansson Haydn as a Birth of Minimal Logic. In the very beginning of the paper, van der Hoven says, the probability of this formula, which is kind of degenerative syllogism, in minimal logic is a desideratum. And why is it a desideratum? Because it stems from the disjunction property. The disjunction property is a property shared by all the usual intuitionistic formal systems. What does it state? It states that if we can produce a proof of A or B, a proof, not just a deduction from something, but a proof of A or B, then we can also produce a proof of A or a proof of B. In fact, we can read off from a proof of A or B, a proof of A or a proof of B. And then the argument goes. So if we can have a proof of A and not A or B, then by the disjunction property, either we have a proof of A and not A, the contradiction, or we have a proof of A. But if the system is consistent and minimal logic is consistent, right, we do not have a proof of A and not A. Therefore, B must be proved. So this is that kind of admissibility argument, right? The argument used by van der Hoven has the general form of admissibility argument in order to show that we have a rule, that the rule is admissible, which shows that if you have proof of premises, then a conclusion. And here is again, assume that you have a proof of A or B and a proof of A. By the degenerative property, you have a proof of A or a proof of B, but then assuming that minimal logic is consistent, we cannot have a proof of A, therefore we must have a proof of B. According to Mark van Acker, this is very interesting. A similar admissibility argument can be attributed to Brouwer, right? And this is a quotation from van Acker. In his dissertation from 1907, Brower gave an account of the hypothetical judgment that served in all his life. On that account, hypothetical judgments made in a certain place have false antecedents, but there is no justification of the general principle x spousal sex or limit. Neither is the familiar derivation of x spousal using the disjunctive syllogism accept the Brower view. So the idea is that we may have some what we call concrete contradictions, concrete bottoms, and from these concrete bottoms we can really construct the derivation of any sentence whatsoever. For example, as in the case of arithmetic, that from 1 equals 0 you can derive anything in arithmetic, but you can really derive anything. It's not like the magic that having a constant for bottom, and from this constant for bottom you can derive anything, right? So according to the a systematic conclusion then is that Brouwer's logic is not really a deterministic logic, but it will be a kind of relevance logic. This is what Brouwer being exposed by Van Acker, right, would be what he calls the familiar derivation. Again, we assume the bottom you have by wicking or disjunction reduction bottom of A, and then you have the negation of bottom, which is a tautology, and then we use the disjunctive syllogism to derive A, and then we can have the principle of explosion as a conclusion, right? This argument is considered a variation of the first modern reconstruction of that medieval argument that we saw, that is that can be found in Luiz' symbolic logic. According to Van Acker, this application of the disjunctive syllogism is not problematic. And again, I will not read completely, but again, the argument is an admissibility argument, right? So you see, if A or B is a description that applies to mathematical construction, then we would have a mathematical construction of A or mathematical construction of B. But if we have a construction of not B, we can't have a construction of B, then we must have a construction of A. Again, a admissibility argument here. According to Van Acker, the problem for Brouwer with this, what is called familiar argument, is not really the disjunctive syllogism. It's a problem of composition of derivation, right? Weakening is okay. If I have a derivation of bottom, I can derive A or bottom. And if I have the disjunctive syllogism, A or B, and not B and A, this is okay too. The problem is to compose these two derivations. It's the composition of these two derivations that would generate the problem that is clearly present in the principle of explosion. I think we all agree that the way I have been presenting these admissibility arguments in order to justify our acceptance of the disjunctive syllogism is, in a certain sense, similar, so to say. Because the last step of the argument in all the versions that I showed you is an explicit application of the rule that we're trying to justify. So in the meta theory is an application of the disjunctive syllogism. So we are using the disjunctive syllogism in the meta language in order to justify the disjunctive syllogism in the object language, right? But I will stop now with this traditional arguments and admissibility arguments, and I will change completely the scenario. I will consider the following scenario, where I will explore the idea of a deduction with the idea of having a trail or a path that you can follow in a walk or in a promenade. Suppose that there is a trail that has a starting point that I will call theta gamma, and then we follow this path, and then we come to a point, which is a bifurcation point, right? That is marked with A or B. From this point, right, one could take the path marked by A or the path marked by B, right? But assume now that there is a signpost, an extra information, not B, that indicates that the path B, right, is closed, leads to a dead end. In this case, right, and I'll show you a figure right now, In this case, the only path that is open to us is the path marked by A. And this can be represented graphically like this. So we start from the initial point gamma, and then we come to this bifurcation point A or B, right? And then we can take the path I, path B, but we have that extra information there on B, saying that don't go there, right? This right path will lead you to a dead end, to a don't go. The sign bottom here simply indicates that we can't go there, right? It's not a logical constant. It's according to an old idea by Newton, it's a punctuation mark, right? It's a sign saying that stop, don't go there, dead end, right? In a certain sense, this is interesting too. In a certain sense, this scenario reminds us of an interesting passage in the very beginning of Brouwer's thesis, the third chapter of Brouwer's thesis, when Brouwer says, I'm quoting Brouwer, the laws of your mathematical demonstrations merely accompany a mathematical construction that is in fact without laws. At the point where we announce the contradiction, I seem to perceive that the construction no longer goes. So again, it's this idea of stop, a dead end, no longer goes. Just a side remark, this scenario, right, reminds us of the very, very interesting remark that Gensius does when he introduces natural reduction, when he introduces the disjunction elimination rule. You all remember, right? The disjunction elimination rule, its usual form, as this form. If I have the derivation of C from A, the derivation of C from B, then from the premise A will be, I can derive C, right? And Gensius says, in this example, an example like this, the tree form, right, appears somewhat artificial, since it does not bring the fact that it is after the disjunction, right, that we distinguish the cases. So Gensius, in fact, was thinking that this formula, in a certain sense, is here on the top of A and B, right? And this is what Gensius says in this passage. So the point of Gensius' remark is that disjunction elimination has the form it has because it is forced by the usual natural reduction system and the basic structure of natural reduction, which is tree, not a graph, for example, right? It's a kind of artificial adaptation to the general tree form. But truly, the assumption discharged come after, as I said there, come after the disjunction, the nature premise, which is disjunction, which is again in this figure. But immediately you see we are going move to conclusion, right? Because we have now the conclusion A or the conclusion B. With this in mind, if we consider the disjunction as a kind of branching point, right? We need, if you want to keep again the tree form, we need some kind of synchronization mechanism to bring the two paths together. So I can see from there, and I must synchronize again in order to go back to simple conclusion. So the point now is that the disjunctive syllogism simply seems to be, to require a new kind of synchronization mechanism, as the following figure shows. So I have A, B, and then I have the path A, B. Path B leads to a dead end. So I go along the path A up to C, and then given that this is a dead end, I just the only path that is open to me is to C. But I think you immediately see that this is not good at all, because we have this connection between the bottom and the C here, which may hidden, so to say, the principal explosion, the expulsion again. So, what seemed to be an application of the disputable group, the expulsion, is just a kind of synchronization mechanism, but it's still a bad synchronization mechanism. Right? A better representation of what is happening in that figure is this one, right? Because that representation is not maybe not the best one, because it can suggest that we could go from that stop point here to C again, right? If we don't want to go to a conclusion, we could try to define a new set of disjunction elimination rules, and this is my first system that I call M disjunction, right? So I have the usual disjunction elimination rule, and I have two new disjunction elimination rules. This one that says that if I have A or B, and a derivation of C from A, a derivation of particle from B, I can derive C, right? And then the same thing for the other minor premise. I have a derivation particle from A and a derivation from C from B, then I can derive C. These, in fact, these rules were first defined by Newton, I think 1978, 1979. Let disjunction be the natural equation system that is obtained from minimal logic M by the replacement of the usual disjunction elimination rules by this new set of disjunction eliminations. It is clear that this system lies between minimal logic and intuitionistic logic. No, I'm sorry. It is clear that there is a proper subsystem of intuitionistic natural induction. But is it possible to prove the full power of X box? Is it possible to prove A implies not A implies B in this system? And we'll see. Yes, we can. Here's a proof, right, of the theorem of the X box in this new system. I have an assumption A, I derive B or B, then I assume A, I assume not A, then I derive the bottom, I assume B, and then I use the new disjunction elimination rules and I come to B, right? And then I discharge not A, and then I discharge A, and then this is a second derivation, doesn't matter first now, right? So I have, it is possible to derive what we shouldn't derive in this new system. But again, if you see that proof is not normal. I introduce A or B, right, and immediately use as the major premise of the disjunction elimination rules. So I have a roundabout, one way in the sense of Gibson. So I can prove that A implies not A, that implies B, but I do not have a normal proof of this theorem. The first derivation is correct. Is that correct? No normal derivation of A implies not A implies. How can we avoid these problematic derivations in this system here? A short digression of relevance logic. Newton's proposal for an intuitionistic relevance logic. Then he proposed the same disjunction elimination rules that I showed you. I mean, these three new disjunction elimination rules. But derivations now are normal by construction or by definition, right? The idea is that you do not allow major premises of elimination rules that are introduced by introduction. So by construction, every derivation is normal. There is no normal legitimate derivations in this system, right? In the case of relevance logic, of course, there is no valence dischargement. But given that you do not allow major premises of elimination rules to be the conclusion of introduction rules, you lose compositionality of derivations, right? Because now, suppose that you have a derivation like this. You introduce A or B by introduction, disjunction introduction, right? You cannot put this derivation here on the top. You cannot compose these two derivations because, again, as I said, it is part of the system that the major premise of an elimination cannot be the conclusion of an introduction. So you lose completely. So the use of lemmas, the possibility of composing derivations, right? Again, this is what I showed there. I have these two derivations, they are correct, right? I have a derivation of A or B from A, and here I have a derivation of B from A or B, which is the syllogism, right? But they cannot compose this derivation of probability at the top of this major premise. The composition is not correct. We can use Newton's idea, forgetting everything about relevance, and define that I can derive A from a set of assumptions gamma even if the derivation is normal. So I do not accept non-normal derivations. As I said, this is a kind of normality by construction, normality by definition. Right? I only accept normal derivations in my system. And this is not the case. If you think about in terms of complexity, for example, we know that non-normal derivations can be much less complex than normal derivations. The process of normalizing may expand enormously the size of derivations. Right? Let me explore now a second, a different possibility. Let's go back to our initial trail scenario, right? Where we had a kind of bifurcation point in B that would lead to path A to path B. But then assume that together with this point A, I use some extra assumption C, that I derive E from these two assumptions. And then we have an extra assumption F, and then I derive G from E and F, and from E and G, I derive H. This is a possibility of a construction, this scenario, promenade scenario that we can have. Right? It is very interesting because if you look at these figures, right, from the point of view of classical logic, right, if I am here, I can see this assumption C, I can see the assumptions gamma, I can see from here the assumption F. If I am here, I can see the assumption F, I can see the assumption C, I can see the assumption gamma, and if I'm here, I can see everything. If we are in the classical logical framework, there is no visibility restrictions at all. I am at this point, everything, every assumption is accessible to me in this point. And this means that I can discharge any assumption. For example, I can discharge the assumption F here, for example. I can discharge the assumption C in G, for example. But in the case, so this is what I just said. In the case of classical logic, there is no visibility, accessibility restriction. In the case of intuitionistic logic, right, the thing is completely different. When I make the bifurcation, right, the splitting point there, I open these kind of boxes here that introduces some restrictions on visibility, right? So if I am here on this point here, I cannot see gamma, I cannot see F, I can only see the assumptions that are used here in order to derive A. And the same thing here. So from the point of view of intuitionistic logic, there's no problem there's a splitting point with the junction. No problem at all. The main problem, right, and we can distinguish, in fact, classical logic from intuitionistic logic based on these dependency relations, on the way we discharge assumptions, right? So in the case of intuitionistic logic, I cannot discharge F here, I cannot discharge C here. In the case of classical logic, everything is available, everything is visible. And we can use this idea now of this box that introduces restrictions on the way we discharge assumptions in order to define the second system. The second system that I call M bottom has the usual disjunction elimination rule, but now it has two new disjunction elimination rules. I have a rule that seems like the previous one, that I have a derivation of minor terms here, I have a derivation of the bottom, and then I come to C. But there are these stars here in gamma and in gamma 2 that I will explain in a moment. And the same thing goes for the other minor terms, right? I have a derivation of the minor terms bottom, I have a derivation of C, and then I can use this new disjunction relation rule to derive C. And again, I have this star here in gamma, and now the star is in gamma 1. The idea now is that this notation, gamma I star, indicates that the assumptions in gamma I are frozen in a sense. And what does it mean to be frozen? That they cannot be discharged below the conclusion of the application of the corresponding disjunction elimination. Let me go back to that picture here. The start, the idea of frozen assumptions is exactly the idea of the box, of putting things inside the box. So I cannot discharge, for example, these assumptions that are in gamma here, right? This is the gamma star that I have in my room, and I cannot discharge assumptions in this box here, right? So this is, I cannot discharge assumptions in gamma, and in this case, where I have the C here, I cannot discharge the assumptions in gamma. Left and bottom be the natural reduction system that is obtained from minimal logic by the introduction of these new rules. The non-normal derivation that we have in the previous system, it's not the correct derivation anymore in this new system. We cannot derive in this new system A implies not A, that implies B, right? We still have the non-normal derivation of not A, B, and this is a non-normal derivation. But this star here and this star that plays a very important part in this new derivation. In order to avoid, again, these not problematic theories, but problematic deducibility relations, we will examine shortly the normalization problem for this new system. We could use, certainly, we could use a strategy similar to the one used by Tennant and restrict derivation to normal derivation. But this I don't want to do. I mean, to impose normalization of normality by construction or normality by definition, right? I can use this definition here that I can derive A from this set of assumptions, even if I have a derivation, normal derivation. Right? But I can use something different. The main idea is this one. Given a certain derivation of A from a certain set of assumptions, gamma, that can be frozen or not frozen, then either pi will reduce to a normal derivation of A, or pi will take us from gamma or from a subset of gamma to the bottom. Right? And this is very nice, right? Because now I allow no normal derivations, right? But then I can use the normalization process, right? When I normalize the derivation, the normalization process will either take us to a normal derivation of it, or it will take us to a derivation of the bottom, to this dead end that is present in the derivation, right? If we look again at our problematic derivation, right, of B from A with the star and not A with the star, when I normalize this derivation, right, I get a derivation of the bottom from A and not A. I do not have a derivation of B, right? I have a derivation of my dead end, the bottom. Some assumptions that were frozen in the problematic derivation may be unfrozen now. And this is a quotation from Don Provis, fantastic God of the Natural Reduction, 1965, where Provis uses this idea of a quasi-deduction. And this is the chapter of set theory in the natural reduction model. Provis says the system F, which is a system for set theory, is to be the system that's obtained from intuitionistic logic or classical logic by the addition of the lambda I and lambda group, which are abstraction principles, right? And then he says a quasi-deduction in one of these systems defined in the same way as a deduction was defined from Gens. A deduction is defined as a quasi-deduction that is normal. So Provis himself opens the possibility of this distinction between a quasi-deduction and a deduction, right? And I'm exploring this idea of having a deduction, right? And this deduction, after the process of normalizing, will lead us to a normal deduction of the conclusion, or it will lead us to a normal deduction of the bottom, right? We could use this idea and say a quasi-deduction in the new system is a deduction as we usually define. A deduction in this new system is a quasi-deduction that is normal. The new normalization theorem established that a quasi-deduction will always take us either to a normal derivation of the same conclusion or to a normal derivation of the problem, right? This is an idea that I like very much. We can think of quasi-deductions, right, as a kind of deduction map, going back to the promenade scenario that we have with we're walking through paths and trails, right? Now we have a deduction map. And once we follow the map, eliminating the detours, we'll either reach the marked goal, the conclusion, or we will reach that end. So we can think of deductions, right, as a map that we can follow. And what is our guide in reading this deduction map? The normalization process, right? When we normalize, we follow the normalization process, we will either come to the place we want to come, the conclusion, or we'll beat some dead ends. So don't go there. This idea of deduction maps cannot be applied. I will skip this one, but this idea of deduction maps cannot be applied to my first system. This is a counterexample of that first system. So conclusions, leading, preliminary, provisory. My general conceptual aim was to examine the possibility of preserving the disjunctive syllogism without having to accept the general validity of the text also, right? The technical aim was to construct an intermediate system between minimal logic, and intuitionistic logic. I have been examining two possible extensions of minimal logic. They, satisfies in a certain way the disjunctive syllogism, do not satisfy in a certain way the external. And this is a kind of a summary of what I've done. In the case of the first system, right, the system and disjunction, it really extends the system and minimal logic. We have these deducibility relations. Compositionality is lost in this first system. In the second system, with the new rules, I do have the disjunctive syllogism in this form. I do not have the theorem of the disjunctive syllogism. I do not have the in this system the derivation of B from not A and A, right? And I do not have the derivation of the theorem, the expulsion, but I do have compositionality. Compositionality is preserved, like in this position. I could add now the DS in this group. It's trivial to show that if I add that admissibility rule for disjunctive solution, it is simply a case of one of my disjunction elimination rules. Right? And future work, as I said in the beginning, the idea is that this is a long slide, I will not read it, but the idea is that I'm present clearly connections with Newton's idea, right? And more specifically with the result that Dennett has, which is based on the kind of extraction theorem. The extraction theorem of Newton has really connections between what he did and what we are doing, right? But there are many differences. Again, Dennett imposes normal form by definition on derivations in this system, whereas our formulation allows derivations to contain maximal formulas. Ours is a logic which stands strictly between minimal and intuitionistic logic, whereas the relation between Dennett systems and those logics is considerably more complex, and etc. But everything here is left to future work. And a lot of things to be done. Translations, system defense, the communism, typing system, the foolproof theory of this system, of the second system. For example, in the case of translations, right? We know that the very general result about translations, if you have a logic L1 and a logic L2, and if you have a translation from L1 to L2, like for example, classical logic and intuitionistic or minimal logic, the double negation translation, the very same translation that takes us from classical logic to minimal logic takes us to any intermediate logic. We can use the same translation to translate classical logic, for example, to custom domain, Dummett's logic, but it doesn't matter. Any intermediate logic can be translated using double negation translation, right? But there's a negative result. if I have a translation that translates classical logic into, for example, intuitionistic logic, take constant domain logic, which is intermediate logic. I cannot use, it's impossible to use the same translation to translate constant domain to intuitionistic logic. I can use the translation to translate classical logic to any intermediate logic, but I cannot use the double negation translation, for example, to translate an intermediate logic to any logic below it, right? So now I have this, I have a translation, a well-known translation from intuitionistic logic to minimal logic, right? This translation translates intuitionistic logic into this new logic, right? Again, because of this general result without translation, right? So there are interesting things, and when we try to look how, in fact, the translation works from minimal logic to this new system, in order to propose an ecumenical system, a new ecumenical system from minimal logic and this new logic that I have. I can use, for example, the system fact, which is Krivine-Girard system F restricted to atomic instantiations, right? In order to model, I mean, the ambition proposed by Fernando Ferreira and Júlio Ferreira was to model intuitionistic logic. But I can model, minimal logic, I can model using fact this new system. I do not have any type of system for this intermediate systems. The foolproof theory must be done. There are lots of things to be done concerning unicity of normal form, etc., etc. So there are many, many things to be done still in this. So thank you very much for your attention.
That's very interesting topic. And then we proceed to the period of questions. We have, I think, 10 minutes.
Yes, thank you very much for this beautiful talk. I have a lot of questions, but I only want to ask two. The first one is about the diagrams you put there. They look like some kind of tableau. But the question is if you can tackle with this kind of diagrams this question that derivations were never really trees.
Never?
Trees. They were never really trees because of the discharging mechanism.
Yes, yes,
You always have the
yes,
discharging
yes,
mechanism.
yeah.
I don't know if you have talked about that, or if these diagrams are, what's the status? Are they formally defined? I mean, the idea, it's very nice.
No, I think you're completely right. When we talk about derivations in introduction, we use that in tree form. But you're completely right. There is a kind of new dimension which corresponds to the discharging, which is, in fact, there's a topological idea in this. Statman explores this dimension of discharging assumptions, which distinguish, for example, in terms of complexity, natural additions and secret couples. Right? So I think you're completely right. In this presentation and in this work, I simply considering a traditional way of looking at natural reduction as trees, and I'm not taking, you're right, I should take into consideration this idea that natural reduction derivations are not really tree, they are something else, they're completely wrong.
Yeah. Can I do the second one?
Yeah.
So if I remember right, Simposio is equivalent to the Shantum syllabus because they both characterize intuitionistic logic.
But that's what I'm saying, that
Yeah,
they don't have to be.
Yeah.
That's my point.
Here is your point, but the question is, if thinking about that, what's the status of, or what is the status relationship between your system and bottom and disjunction?
They, I can show you the last slide, right? Next. But I have a summary of what I can define in each system. For example, in M disjunction, right? I can prove this theorem, for example, right? In the M bottom system, I cannot prove this theorem. So they already distinguish in terms of what I can prove in the system. In the This is not apparent in this new system because of that restriction of discharging of assumptions that the frozen idea imposes, right? So this is an interesting difference. And again, and this for me is the most important thing. In the end document, I have full compositionality. I do not have any restriction concerning compositionality. If I take new tenants idea and explore it in connection with my system and the junction, compositionality is constant. If I define deduction as being normal by construction, then I do not have composition. There are ways of recovering compositionality, and this is one of the things Newton does, because it's horrible to lose compositionality. And then his extraction theorem is a way to recover in the case of intuitionistic logic compositionality. But I have compositionality from the beginning in this system. In the other system,
Thank you very much.
Thank you.
Thank you so much, Mr. was a really good presentation. Of course, you are working in natural deduction.
Yeah.
But my question is, if you analyze these kind of connections in the case of sequence calculus, my concern is about transitivity of the deductions, and if you need transitivity.
Yeah, exactly. If you do a sequence calculus exploring Newton's idea, you lose cut. We don't have a general cut. In this system, in fact, this is a very good question. In fact, the inspiration for this, let me go back again to the. Yeah, the inspiration for this idea of these boxes comes from sequence calculus. From a system for intuitionistic logic I have together in Valeria, which is called field with just one L, to distinguish from field with two L's of linear logic, which is a multiple conclusion sequence calculus, right? Where the only place. You remember that Mahara system of sequence calculus for intuitionistic logic. Yeah. What Mahara does, he allows multiple conclusion and then restricts the consequence to one formula, just in the case of implication and universal quantifier, right? In our case, in the case of propositional logic, even in the case of implication, you can have implication to the right? It is, but you have to control dependency relations, right? And these dependency relations is exactly what is playing the role here. Right. So you're completely right. Inspiration for the idea of having this M-bottom system comes from sequence calculus.
Questions?
So you can take and then you have, from gamma you can conclude A.
Okay.
You can interpret this inside the logic as you can interpret this as the conjunction of formulas and gamma implies it, right? So you have this interpretation of sequence inside the logic itself, right? Do you have anything like this in the system?
No, you don't have this.
You do not have.
Exactly, because some formulas in gamma may be frozen.
Yeah, but I understand the program, but in the other one, the first.
The older one,
Yeah.
there's no problem at all. But you must pay attention to this idea of compositionality. But if you have a real deduction, which is normal, then you can have no restriction. If you have derivation of A from gamma, you can always do this. Take the conjunction of the assumption in gamma, and it will apply.
Yeah, I guess so. So that's
Yeah.
I guess because I'm puzzled.
But not in the second system.
No, of course in the second
Yes.
just puzzled because I fail to see when you do this kind of things, and then you should be able to use cards. So
To use what?
cards. So
Good. Yeah.
card is going to fail somehow, somewhere, and I would like to understand better. But this is my
If you were to replace
I have some public hearing.
Oh, if you were to replace like in the Yoga, you replace like one person with the boxes instead of the individual things, would that work better or? I'm sure. Okay, so it's like your first example is like you're using the boxes to like describe that, right?
Yeah, that one.
Like your,
The box.
yeah, like you have those boxes as part of your assumptions. But instead of individual.
I'm sorry, still. This is not your.
You take off it.
Yeah.
Sure. Could you just use the boxes as your assumptions, like you can have to incorporate boxes into your assumptions and just have it.
Yeah. It is incorporated into the idea of the star. The idea of the star incorporates the box. So that's the role that the stars that I put in. Yeah. Those are stars that you see there. They corresponds to the box. So I'm putting everything below gamma inside the box that I cannot discharge the assumptions in gamma. So you can see here, like the box here, that gamma is forbidden, so to say, in this gamma. So this can be yeah, and that's fine. I cannot have this result. That Elaine was saying. Because I would have to discharge. Even if I have the something with frozen here, I would have to make the conjunction and then to discharge. But I cannot discharge this forms because they are outside the box. Okay.
Perhaps not a question, maybe an opinion from
Yeah.
I was looking at your deduction map in one of your systems. Do you think it would be a good idea for a student project to kind of invert the deduction map? You know, the tree, put it upside down and create like a water system where the A or B, it's a system where if water comes from one side, it opens, or it comes from the other side, it opens and continues the flow. And in A and B, the system will only open if both waters hit the little thing, and then the water comes. And if the water arrives at the bottom, then that will be like the proof that thing is true or something. It's a possibility.
So you're proposing to put it upside down?
Right, I put water on the top, so it arrives at the bottom. And if you have B or not B, maybe like water comes only in one direction, can you travel into both? I don't know.
Yeah. No, just first impression. If you put everything upside down, you're very close. Someone said that very close to tableau in a sense. If you just put it upside down in a sense. Maybe. Thank you.
Well, thanks a lot.
Thank you.
It's a pleasure and an honor to introduce Professor Elaine Pimentel of University College of London. She's going to give us a talk on ecumenical systems, motivation of this definition, and its relationship to mathematical axiomatization. Professor, please.
Thank you. So just a disclaimer. So this talk is supposed to be like for all. So if you know about, ecumenical systems or proof theory, you're an expert in that, you're going to be kind of bored for 95% of the talk. If you don't know anything about that, then this is for you, right? Because I assume that people, most of people do not work on theory. So I'll go, gently and talk about this. Read this one, okay? So first of all, this is a drawing board with many people. I put there Luiz, Sonia, and Emerson. So Luiz is Luiz. Sonia Marron, she's a French researcher, a professor at the University of Birmingham. And Emerson was my master's student now. He's doing a PhD in Sasso in Italy. And there's a little bit of some things that I'm going to talk also from a work that we did together with Valeria Pimentel. But the whole of the work is more with this three problems. So I was talking to Christina yesterday, having dinner, and having some wine, talking about logic, about life, about everything. And then she was saying that it's really difficult for us inside, as people that do mathematical logic, to talk to each other, right? And at the beginning I said, no, come on, don't say that. I almost cried. And then I thought a little bit about it, and she's completely right as always. So why so, right? So here I put the four. I told her yesterday that I consider that mathematical logic is based on four pillars: model theory, set theory, proof theory, and recursion theory. Okay? Valeria disagrees, as always, and she said that it's 5 pillars. We should put complexity theory as there as well. We and I disagree. I don't have a strong opinion about that. So let's take a look a little bit on what these things do. So if you take set theory, and this was the subject that Christina talked about this morning. If you take the objects that we study, so we do study mathematical objects, right? So which one is the object of study of set theory? It's sets, right? And what do you do for studying that? Well, you should, for example, you use functions, right? So she showed us lots of functions today on her talk. In modern theory, that I would guess if I ask you who does modern theory here, and be almost everyone, right? So if the objects are models and theories, right? Then some tools that we use are, for example, definable and type-definable sets. Just to put some, okay? This is not for to put everything. Complexity theory, so you have algorithms as objects, and you use time and memory, for example, to study them. And recursion theory, you study computable functions, and for that you use algorithms, for example, and proof theory. And this is what I'm going to talk about to you today. What we do is to study proofs, okay? And what we use for study proofs is formulas, different kinds of formulas. Okay, so today I'm going to talk about proof theory. So sorry for the ones that do not do proof theory, but as I said, it's going to be general kind. Just at some point, I'm going to describe the sphere, but I'm going to warn you, and then we can do something else. So what is proof theory? So what kind of objects we study, what kind of proofs we study, and how do we do that, right? So let's start with very basic kind of foundation. So let's start with this theorem one. There exists x and y in both reals, irrationals, such that x to the y is a rational. So this is a theorem, right? So I guess that most of you do know this theorem, maybe with some other, let's say quotes, like, but I think that everyone here knows this theorem. It's really simple to prove, so I put it here. So you consider, sorry, if I put, okay, so you consider A as, you consider square root 2 to the square root 2, okay? So there are two possibilities to that. Either this is rational number. In this way, in this case, you're done, because you take x and y as being square root 2, and we do know how to prove that square root 2 is irrational. And then one to the other will be rational, and you're done. Or in the other case, so it is not rational, so that it's irrational. And then you're going to take x as the square root 2 to the square root 2, and then you take y as the square root 2, and then x to y is going to be 2, and 2 is an integer, right? It's natural. So you're done, right? So this is a perfect, clear, simple proof, right? A classical mathematician is going to say, well, cool, it's a very nice, simple thing that I can, show to my students, and it's really cool. The stupid mathematician is going to say, wait a minute, this is really strange. I mean, which one is true? Is square root of 2 to the square root of 2 rational or irrational? You have to tell me that. Before you tell me that, then I do not agree that this is, I don't accept it at all, right? So this is what I'm going to talk about today. So if you never heard about this classical intuitionistic, you can think like classical is like we are classical from, I don't know, when we are born in mathematics. Intuitionistic are, they need, for something to be called a proof, you need to show the proof, okay? So this is not a proof intuitionistically speaking. For an intuitionistic mathematician, it's not going to be, okay? And then you can say, but we all know the answer. We all know that actually is this that happens, that if I take square root of 2 to the square root of 2, this is irrational. Okay? Why? Because this is exactly the 7 Hilbert's problem. Well, it's an instance of that, right? And this is the problem here, that if you take alpha and beta to algebraic numbers, with alpha not 0 or 1, and if beta is not a real rational number, then alpha to the beta is transcendental. So it's more than irrational, it's transcendental, right? And then, so this is the Hilbert's second problem. Well, then here, so I took this text from Elaine book. This is 3, so it's okay to put it there. But I didn't go through all the details. I understand the idea of the proof. So the idea is to transform the theorem into something equivalent, right? And here I already use classical reasoning to do that because you use positive thing. And then he goes on, and then there are many lemmas, so I'm not going to show you. I mean, it's huge. You see, I skip it many pages here, 10 exactly. And then you get to the end, and then this is the last, this is the end of the proof of the last lemma to prove Hilbert's 7 theorem. And if you go here, you see, but this is a contradiction. Oops. So we do know that this is irrational. We do know, but the proof is what? By contradiction. Okay. So an intuitionistic guy would say, role inhabited work. Well, it has been used in religion to say that, when Catholic religion to say that the Christians from different kind of views of Christianism could, sit down together and talk. I don't kind of like this thing that the role inhabited work. And the way we understand, Luiz and I, ecumenism is the search for unicity. When exactly you can have different thoughts, ideas, or points of view living together peacefully. Okay? So this is the idea. So in this talk, I'm going to talk about ecumenism and what they are, what they're for, why should I be interested in that, and what's the motivation behind the definition. And I'm going to do that only for classical and intuitionistic logic or systems. Okay, so this is going to be the talk. There are some motivations for doing that. So why we do that? So first, so this works based on a work that was published at Providence in 2015 on the book of the press script for Luiz. And his main motivation was philosophical, and what he was looking at for was the meaning of the connectives of the logics using only theory or using only the rules that define those connectives. For this, you need several things that you need that your system have many features. So, for example, harmony and separability should be pure. I'm not going to tell everything about this. If you do know what these are, then good for you. If you do not know, it's not important for this talk, for this talk, this one. So this is what Providence was looking for. And then Luiz gave a very nice logical motivation that I really like. There is a dialogue between an intuitionistic logician and a classical logician. So the intuitionistic logician is going to say that if you say to me that A or B, and by that you mean not A and not B, then I accept that A or not A is better. Okay? So if you do know logic, so this is the principle of the excluded middle. And what this is saying is the intuitionistic logician is saying that he can accept that if by that he means this, right? So they agree on that. Okay. But then the classical logician say, wait a minute, so this is not really quite that, right? I do not want to, because what I'm doing here is doubling everything, right? From here down. So I do not want to take this and then double negation, and blah blah. So to put not A in front of everything, and see this as this, for example, right? It's like too much, right? So, for example, when I say that Goldbach's conjecture is either true or false, I'm not saying that it would be contradictory to accept that it's not true, and that it's not the case that it's not true. So complicated, right? So I don't want to complicate things. So classical logicians say, okay, we do agree that I don't want to complicate things that much. And then another feature of ecumenism is that, as you're going to see, we're going to separate the connectives at some point. I'm going to say, okay, we're not talking about the same thing, so they're not the same connectives. So let's separate them, right? And then the intuitionistic logician can say, okay, but this is why you're doing that. At the end of the day, instead of having conjunction, disjunction, negation, implication, etc., you can have only, as Shepherd's stroke or Klein's dagger. It's a connective that from that once either of them, you can generate all the others. You can generate conjunction, disjunction, negation, etc. And then the classical logician is going to say, not at all, not at all. I mean, you can have one single connective that describes everything else. It doesn't mean that the other things don't have life by themselves, right? They have meaning by themselves. Proposal of life, let's say, right? So when you say something like A or B is equivalent to not A or B, three different operators here. That'll be the disjunction here, the negation, and the conjunction. Okay, each one of them, they're different people, and they have different meanings, right? So the goal of the logical motivation behind the word thinking is also to explain this different, even though you have things that are equivalent, they're different in nature, right? It'd be like when in mathematics you have isomorphisms, very beautiful ones, right? But they're not the domains that you're talking about, they're not the same. They are isomorphic, but not the same. I mean, they have their own life by themselves, right? They can be interesting by themselves, right? Okay, so this is the first time, I've been talking about determinism for a long time now, but this is the first time we do it live. So let me try to interact with you. This is going to be new for me. So what do you think? So we've been talking about theorem and blah, blah. What do you think about this? Is this a theorem or not? So if x plus y is equal to z, then x is the greater or equal to z, or y is the greater. What do you think?
Yeah, this is there.
You think it is? Okay, who else? You think? Okay, you too. You're classical mathematicians. There are two things here. The first thing that is missing, I never told you what's x, y, and z, right? So let me get it better. So they're real numbers, okay? So if they're real numbers and you're classical, then the answer is yes, okay? If they are real numbers and you're intuitionistic, then the answer is no. If you're intuitionistic logician, mathematician, and the numbers are natural, then the answer is yes. So you see, it makes a difference, right? The domain that you're looking for and the way you see the thing. So that's why I do this, we all did this kind of tests, right? And you have to see little letters, blah, blah, blah. So if I put here that this implication is intuitionistic and this OR is also intuitionistic, then the classical mathematician is going to be sad because he doesn't understand what intuitionism means. And the intuitionistic mathematician is going to be sad because this is not a theorem for him. It doesn't make any sense. Okay? Right. So what did I say? I told before the dialogue, Luiz dialogue, that I could put double negation in front of things, right? Right. So if I do that, then what I'm doing is to transform everything to classical. So I have a classical implication here, and I have a classical disjunction here, and then I put the glasses classical glasses here. So the classical mathematician is going to be happy, the significant mathematician is going to be happy because he is going to understand this. Now, finally, makes sense to me, right? But we can do better. We can be inclusive, right? And we can have ecumenical glasses. What ecumenical glasses can do is to see that here you need to be classical, for example. If here you are intuitionistic. So if you want your implication to be constructed, it has to deliver a proof. Then for both to be happy, this has to be classical. Okay? So you're doing better, right? You're going to be extra even. Okay, so what I'm going to talk about is what makes logical connectives classical or intuitionistic. And you can ask yourself, like, why do I care? I mean, I'm a classical mathematician, right? Who cares? Yeah, so the thing is that I don't know about you, but I think it's really beautiful when you prove that A implies B. Normally, we can do that like in that direct mode. You can do that by contradiction or by contraposition, right? I am one of this kind of mathematicians, if I can say that I'm a mathematician at all, that I prefer every time I can put a direct proof, I prefer, because I understand the proof. I understand what I'm doing. I'm constructing something. By contradiction, for me, is worse, because I don't have a clue on what I'm doing. And biproposition is something in the middle, where you go from here, from A, you go to a certain point, from B, you go backwards to another point, and you find yourself in the middle somewhere, right? So to think through mathematical proof, I'm talking about mathematics, so you take mathematical proof, and to understand where you need to be classical and where you can be constructive, this is kind of nice. It has many applications actually when you are going to formalize proofs like in Core or Leon or any proof system that you like. Okay, so it looks like a lot of things, but don't worry, it's not going to be hard. So proof theory, it's all proofs, as I said, we are worried with things like when I choose people, or when can I transform one into another? Can I identify patterns of groups, this kind of things? We need a formalism to do that. So we need a purely mathematical language, and this is proof theory. And there are many applications. I'm not going to talk about this. Let me just explain to you how things would look like, right? So we mathematicians, we combine lemmas in order to produce theorems. So normally we prove something that we call a lemma, but it's a theorem that we call a lemma. And then if from this lemma we can prove B, then actually we don't need this lemma. It's there. It makes our life easier. It makes some books that you look at the book and you say, how come this guy came to this, right? To this conclusion. Many lemmas, how come, right? Or when you're learning analysis for the first time, and you have let delta equal to epsilon divided by the square root of b divided by 47, something like this. Where does that come from, right? Normally, so the books, they are organized, so you don't see these things coming. They are really organized, and the work's done, right? So that's logically what mathematicians are doing is to exactly to use this group here that we call cut. It's called cut in the sense that you actually cut this A with this A here, right? The hard parts kind of lemma. So I'm not going to say we. I mean, you mathematicians, you're smart, so you find this lemma. But for example, if you ask for a computer to find it, then it's going to be complicated. So as I'm interested as well on things that we can implement, this is not a good group to have in your system. So using lemmas is not something that okay. So let me just show you more or less what kind of reasoning we do from practice. So I'm going to talk about simple things. So propositional logic for now. You have propositional variables like atoms. You have the connectives, the ones that you all know. I didn't put notation here, but so you can vary the connectives here, and then you have the formulas, propositional formulas, logical formulas here. And then you need a way of a system, a formal system to reason about this, right? One way of doing that is to use what we call Hilbert calculus. And Hilbert calculus for this very small fragment of inductionistic logic works like this. I have two what we call axioms, or let's call it axioms or schemas. That will be this one that you always accept. You're always going to accept something like this, and you're always going to accept something like this, whatever it means. And you have models warnings, it's easier to understand. So if I can prove A plus B, and I have a proof of A, then I have a proof of B. And then other derivations are finite sequences of formulas where you're going to instantiate the things with these formulas, and you can only use models. So let me give you an example. So if I had to prove A implies Z, what's A implies Z? I want to prove A, and as hypothesis, I have A. This should be simple, right? Before coming for this talk, the first time I was going to give this talk, I tried to prove this. I couldn't. I felt really stupid, but I'm not stupid. So this is the proof, right? So what you have to do is to take these two schemas here and instantiate. So the first instantiation, the first thing that you instantiate is this X here, and this A you're going to put A here, this B here you're going to put B place, implies A, C is going to be A, and there you go. So why on earth we have this thing? I don't have it. Only because it proves that we have it, right? But there is no way of saying what kind of I don't have an algorithm or a common sense to say, okay, instantiate this like this, and then this like this, but then you're going to instantiate this like this, completely different way, and then you use models to execute this, right? So this is not a good system in many ways. The first one is because you cannot tell people how to construct derivation. It doesn't tell anything about complexity, so you don't have a clue how complex it will be to put A plus A. It doesn't have any structural relationship between the thing you want to prove as a system and the steps that you do. You don't know how to associate things, and it's really difficult to find which axiom I'm going to use where and which instance. I put some colors there, only for me to understand more or less where I was doing what, but then this is really complicated. So there are exceptions. So once I saw talk from Marcos, and his system is a Hilbert kind of system, but it's something that I can understand. It looks like a tableau more or less. So I do not understand that. So there are some other formalisms that we can use. So one would be net reduction, and the name is net reduction because it's a deduction, it should be natural. So it's more or less the way that a mathematician will think. And this is for intrinsic logic, for example, is based on Brouwer-Heiting common conditions. The conditions are really easy. So let me explain using already the formulas that I want to show you slowly. So the first thing that they say is that a proof of P, A and B, is given by presenting a proof of A and a proof of B. Makes sense, right? So we're going to write this way. So if I have a proof of A and I have a proof of B, then, so this bar here is then, I have a proof of A and B, right? I can do the same for disjunction. So a proof of A or B is given by presenting either a proof of A or a proof of B. So if I have a proof of A, then I have a proof of A or B. If I have a proof of B, then I have a proof of B as well. And the implications like the proof of A plus B is a construction, could be a function, or we are in deterministic, so it's a construction which permits us to transform any proof of A into a proof of B. And this is represented like this, so it's already, had some figures like this. So if you have a proof of A, you have a way of transforming this into a proof of B, then you have a proof of A into B, right? So these are called introduction rules because from top to bottom, where I'm introducing some connected, so that's introducing here junction, identification. Then we can have the elimination rules using the universal principle. I'm not going to stop on this, just to say that there's a way from this one, and using this principle, I can do the elimination rules. So for example, if I take this one and I use this principle, I'm going to have separate modulus points that you already saw. And then the derivation is going to be a 3. And if I want to do A minus A, then it's this rule. Let's be honest, I mean, this is easy, right? Right. The problem is to prove analyticity, it's called normalization, the same. I'm not going to enter into details, but then this sometimes is problematic to do. And Genser himself, when he proposed a net reduction, he proposed another formalism that's called secant calculus that allowed him to prove normalization. Now it was discovered that he had already a proof of normalization, but this was discovered much later. The thing is that here, instead of having the things discharged somewhere up there, so you have your assumptions here, instead of putting them there up there, you go with them all the time. So you want to put B as a consequence. This is a matter simple consequence. This assumptions here, you go with everything together. So you carry everything. You carry the information you have, you carry the information you want to prove, everything at the same time. And then you're going to have right rules and left rules, not an introduction and then rules, right? And then the limitation is going to get through as well, and it's easy to prove the idealization. This is simple as well. Analyticity, every same as determination, so we don't want to have this, but this is normally it's boring to prove, but normally it's straightforward in the sense that you have to do many cases, but at the end we're going to see. And good thing about this is that once you have a proof that's ready for three, then you can tell many things about the system. So for example, you can talk about consistency, scalability, complexity, interpolation, whatever it means. You can have automated the deduction procedures only with systems like this. So, when you change from one system to another, it's not only a matter of taste. It's also, it depends on what you want to do. So for example, if you want to implement something, I would say that secant calculus is better than natural reduction. If you're a mathematician and you want to understand the proofs, then I would say the natural reduction is better than secant calculus. And in any way, I think that higher Hilbert systems are better than anything. So I'm more almost at the middle of the talk, but I'm going the second part of the talk. I'm going to stop at some point. I'm not going to stop everything. So what's about the cumulative? So for a classical logician, they are not make holds. We already said that. For a inductionistic logician, it does not. And why and where it does. So if I take the secant calculus and I try to prove A or not A in secant calculus in a secant system, then well, the most common system used nowadays for classical logic, the rules are really simple, and the thing is that the OR on the right is the same as common, so you can always go up, put a comma here, then negation goes to the other side, and then you finish the proof because you have what you want to prove you have as a hypothesis. So the proof is easy. If you try to do the same with inductionistic logic, you cannot, because here the junction is not the same as the comma. You don't have a comma there, and then you stop, and you cannot prove that. Solution that Providence gave is that they are not the same. So they are not the same. Okay, right? So, and I quote, the classical logician is not asserting what the inductionistic logician denies. The classical logician asserts that A or classically not A, which the inductionistic does not object. He objects to the universal validity of A inductionistic or not A, which is not asserted by the classical logician. So they are agreeing on everything. So you see, we already have, nice way of talking, right? We just need to identify the connectives that they are not the same for classical and inductionistic. Each one of them, they're going to have their own, and it's going to work, right? So don't be scared. I'm not going to, start presenting systems and blah blah. It's only for you to have a clue what's going on. So this is not the whole system. So this is private system part of the system. So there are some connectors that are shared. So for example, negation, conjunction, and for all, now going for first order, they are the same for the inductionistic and classical mathematician. The classical has its own implication, disjunction, and its extension amplifiers. So has the inductionistic logician. Okay. So this is Providence system, part of it, and it has some problems. So for example, for defining the classical connectivity, you need to use negation all over, and this is not good because the system is not pure. So with Luiz, we just submitted a paper where we don't have negations anymore, but the price for that is to put an extra context here, so I'm not going to explain that to you. So this is called the scoop. If you do know the works of Jihad, then you know what the scoop is. If you don't know, it's okay. It's completely fine. Just to say that if you go from this system to this system, the difference is that here you don't have negations,
big thing. So happy to be at the end. The idea is that formulas are going to be worked on the scoop. Formulas are going to be chosen to be focused on. So you have a notion of normal proofs, normal proofs in the sense that you choose what you're going to work on at each point of the proof. And you can store formulas if the formulas are classical. So you have this thing instead of putting negation, you just store them and let them there. And just at some point you're going to what? You're going to focus on it and work on them. So you see, you have a path that you do. You have an organization of proofs. This is really good. I guarantee you. So just to have an idea, this is the proof of Peirce's law in one system of natural reduction for classical logic. And what I don't like is that you want to prove A plus B plus A plus A, and you have to use negation all over. So this is not natural. With our system, we don't have negation, so implication is implication, and we just use rules for implication, never for negation because we don't have negation. And the second beautiful thing about this is that, as I said in the beginning, there are some points of the proof that you can be classical or inductionistic. So this is the first law, classical, but if you change this to inductionistic and or this to inductionistic as well, you have the same proof of the thing. So you see now you are ecumenical in the sense that the only classical implication should be, for this formula to be provable, should be this one. The other ones can be constructed, right? So it's nice. So when you're proving something in your theorems and you use something like this, in mathematics, for example, you know that this step can be constructed, this step can be constructed, this step has to be classical. So here you're going to have to use either absurdity or contradictivity or this kind of things to be able to prove this thing. Okay, so I'm not going to talk about this. You can do normalization in this. So and this was Luiz. Of course, I'm not capable of doing that. But, this is really a team kind of work. We can also do sequence calculus, as I said, it's another formula. Now we can do the same using negation, and then using this system, I can prove. Remember Emerson's example at the beginning? X plus y equals to z implies inductionistically that x is greater or equal to z, or lastly, y is greater or equal to z. You can do that. You can prove this using a proof system, right? This is really cool, and you can automate this proof. This is really easy as well. We can get rid of the negations. I'm not going to talk about this. There are many things that you can prove. There are many things that you cannot prove, and this is also cool. I mean, normally it's complicated to say I cannot prove that. You cannot prove that because you're not able to prove that, or you cannot prove that because it's impossible to prove that. So when we have the right formulas and we have the right way of saying things, we can have negative results as well. It's impossible to do this, right? So this is nice. This is something in mathematics that is really important to prove that something is impossible. It's impossible to do that. But normally it's complicated to do that. This is something that I asked Luiz now, but I'm not going to into details. Is that actually the symbol, the consequence symbol corresponds to the inductionistic implication. But if this formula is classical, then this is going to transform to classical here. So this is really ecumenical. So the entailment is completely ecumenical because it depends on what you want to do. So this is nice. Okay, so I'm going to spend the last 10 minutes talking about modalities. I'm going to do that in a very, so this is like the second part of the talk. And I'm going to do that really slowly, okay? So what is modal logic? So I was talking now about classical and inductionistic, propositional at first, then first order logic, right? And modal logic. What's modal? So let's take this sentence. Carlos Hansen. Carlos, you. What can we put there in this blah? No. So Carlos is handsome, right? I can do that. What with that?
Calculus handsome, right? So classical logic is about truth. It's going to talk about truth. So this is a sentence that's going to be true or false, right? It depends on who we're talking about. We can say it's not, right? Yes, yes. But I can do something else. So I can qualify truth. So I can say Carlos is necessarily handsome. So for example, if he's going to be a model or something like this, right? Possibly handsome. I don't know him, but I guess that he is and he's possibly handsome. This is called dialectic interpretation, right? Of the truth. But you can also have something like Carlos is known to be handsome by someone. You need to have mentioned, so for example, by me. So this is extended interpretation. You can have doxastic interpretation. So for example, Carlos is believed to be handsome by someone again. He's obliged to be handsome and he is a model of something. Or you have relation or related to, then you have the interpretation. Okay? It's now handsome, will be handsome, someone in the future, it's the same interpretation. This is not a logic, right? You are going to, what you're going to do is to qualify truth. And there are many ways of doing so. Okay? So let me stick with the first one. I like interpretation, Carlos is necessary with handsome. Let's see this in another way. Right? I'm going to put the necessary in. So necessarily Carlos is handsome. Makes sense, right? But then Carlos is handsome is an atom, right? It's a formula, atomic formula, right? A propositional one that we already saw at the beginning of the talk. So if I call this Carlos is handsome as P, then I have necessary P. And I'm going, instead of writing all the time necessary, I'm going to put a box. Okay? Box P. So this is model logic, possibly the same thing. I pass possibly to the beginning. I call this P because it's predicate and I put time, right? Because girls like a lot of time. So then you have possibly, right? So what about, so I said that how come? So when you take prepositional classical logic, you have you can find things using, you can find meaning of phonetics using the truth table. Like this, for example, this truth table for implication. So suppose that you have PQ, so this is the truth table for PQ. What we're going to do in modal logic is instead of having one truth table, I may have many, right? And in each place that I have a truth table, I give a name to this. So these are called worlds. Okay? So for example, I can be in a world where P is valid, so valid is 1, Q is false, and then P plus Q is going to be false. Okay? But I can be in another world called B, for example, where P is false, Q is true, and then P plus Q is going to be true. Right? So it depends where I am. Okay? In each word, I can have different meanings for the same positional variables. And I can relate this word. I can say, okay, from this word here, I can see this one. So I can see words, right? So I have relations. So it's really a relation that we are used. And we may have that a word can see itself. So a relation can be, for example, reflexive. Thank you. For example, right can be transitive. We can think about relations. Okay. So this gives this way of looking at the monologic is interpretation. And I was not planning to talk about this anyway, so I'm going to finish. It's just to tell you that you can, so you have a model behind it. So you can study this using this kind of models. It's called empiric models, right? If you do model theory, then there are other ways of looking at the same thing, using, for example, high-T algebras or something like this, right? But I'm not going to talk. The talk is not about this. The talk is about this. So, how can we see modal logic with ecumenical eyes, right? what we do is the following. We're going to interpret the box as I will take the semantic interpretation of the box and I'm going to talk this out loud. When I do that, I use first order classical logic, okay? So box A is valid in number X if for every word Y related to X, A is valid there, right? So I'm saying out loud, right? So this is the interpretation of box. I have the interpretation of diamond, one is for all, the other one is exists. And to see this in an ecumenical way is, remember that for all, we only have one, it's shared. So I'm not only going to have one box. Exists there to classical and intrinsic. So we're going to have a classical, the ecumenical view of this is we're going to have one box and we're going to have two atoms. So we have one way of necessarily doing something or looking at something, and two ways of possibly seeing something. One way is constructive and the other one is not. So this is the thing. So this is the whole idea. So I'm not going to enter into detail. So you can have semantics behind this. So we have a ecumenical bi-relational structures, whatever it means. We have also rules, of course. We have extensions, so we can talk about these relations. If it is reflexive, transitive, or it's confluent, or it's symmetric. And then we're going to have a formula behind it, and then we can transform this formula into rules as well. So then we have a way of reasoning about all these things, like in an automatic way. And we can have theory with this, but I'm not going to talk about this because it's not interesting for this particular audience. Here, I wanted to give you a glimpse of what the proof would be. So I can prove that not box, not A implies classical diamond, for example. And this is expected. The other way around, you cannot do it, okay? So, to wrap up, ecumenical systems may help us to have a better understanding of the relations between classical logic and intrinsic logics. This is nice because when you take a mathematical proof, you can say exactly where the proof is intrinsic, classical, or it doesn't matter. I didn't discuss the nature of atoms, but this is something that I've been thinking a lot. So, as I said, when I asked it to you, if something was a theorem, and I said, it depends. If we're talking about real numbers or natural numbers, we're going to have different answers. So, this is all about the atomic things that you have in, right? We've been making other approaches, so we only have one negation, we may have two, etc. When we talk about model logics, I didn't talk about constructive model logic. Actually, I didn't talk about model logic that much, but well, I could have done a better job on that. We don't have people. We don't have algebraic ecumenical models. So, who's going to do that? No, you. Someone that works on model theory that wants to do the algebra part of this. We don't have it. I don't have a clue how to do that. Well, I could do the simple try of doing a Lindenbaum algebra or something like this, but I'm not an expert. And talking about typing, I need to make Danielle Ventura happy. We have a typing, so I know that's not, you're not interested in that, so I'm not going to get into details, but for you that do understand this is a mu calculus, you have a mu lambda calculus with configurations. So we're doing work with LFS and now on that. Muchísimas gracias.
So we proceed to the questions.
Yes. Have you tried to do the same in this ecumenical system with labels? Like I was thinking about, for example, Gabay label development systems. I know that there is a paper where they have the same system with labels for intuitionistic logic, classical logic, and some structural logic. And I was thinking that about the previous talk, that probably these boxes you can do similar stuff with
with labels, right?
Yeah, so, yes, so I didn't talk about this because I passed it through this and bullet. But, so for example, in the model system, it has labels, right? In the propositional system, we could use labels as well. But actually, we do have a system. We did all the systems we could, like with labels, without labels, with nesting, without nesting, hypersequence, everything. But it's different from the label systems that we talked about. So it's not the same. It's not the same system, and the idea behind it is a little bit different. But yeah. So and in the model case, we started with labels because this is a way of relating the semantics with the internalizing the semantics inside of the system. But actually, we can do better. We can shape up the labels. It's here, but I'm not so that is using, instead of having a sequence, we have trees of sequence. So what we call nested systems. So then you take off the labels. So labels. So you use labels for. Okay, so the use of labels by for example, has had many criticisms because you're kind of making your system, polluting your system, if you wish, right? So what happens is that when you talk about labels, where are the labels? They're not. So this is not part of your grammar. It's not there. This is only a predicate that's going to interpret the relation that you have in the model, right? In the model, right? But this is, you see, you're polluting kind of the system, right? So there is a criticism about this as well. So everything that we did for classical and inductionistic logic, we did without labels because we don't need them, and this is good. You can internalize the things. So this is the thing. You can here. Everything that I said, you can represent like this with the inductionistic arrow here, right? So in this way, you're having what it's called internal systems. They're cleaner, they're easier to handle, they're easier to implement as well, right? There are some cases that you cannot, that you do need to put the label there, or at least no one knows how to do things without. So for example, if you take intermediate logics between inductionistic and minimal logics, between inductionistic and classical logics, there's no way of doing that, at least as far as I know, using sequence without using labels. So you need them. So there are sometimes you do need them. There are sometimes you can avoid them. We avoided everything every time we could until we got here. But then we managed to avoid as well. So at the end. But then the structures got more complicated, and it's more complicated to explain that. So I try not to.
Can I take some questions?
Sure.
Just I was wondering about like algorithmic behavior, right? Like for example, these systems by the way, I mean, probably they are not pure, but algorithmically this system, which is based on K, like like has some complexity advantages. And I'm the kind of logician that says that one of the pillars should be also complexity. So yeah, so this for example, when you have the cost-based system, you can improve the behavior algorithm.
We can do the same using nesting. So, but then actually we have not with Luiz, but I have some other work with more logics where we have optimal proof systems for several kind of model logics, more blah blah blah. They are based on extensions of sequence, but then they're optimal in the sense that they're as good as it gets, right? When you do proof search, you can do that in a minimal way, in a way that you achieve the minimal complexity of proving from that logic. Sorry, system matches the complexity of proving something. Yeah.
Thanks a lot.
Thank you for the talk. Obviously,
Already saw this how many times? 3
Ecumenism is about communication between system projects. But what about disagreement in logic? What do you think about that?
Oh, come on, let's say peace and love. Yeah, this is a good question. So, with Luiz now, we've been, asking ourselves other kinds of logics. If we could combine, or would it be impossible to combine them, or what happened? Yeah, we don't know. I don't have an answer.
This is something about the case of the inductionistic logic and the classical logic. Maybe the problem is about multiple and single conclusions. Both systems agree about some structural characteristics of the sequence or this kind of stuff.
Yeah, you're right. So when we did the natural reduction with Stu, this is a single conclusion, but it's like a cheat kind of, because you have the classical context that you put there, where you collect classical information. Yeah, and then when I gave this talk, not this talk, a proof theoretical kind of interpretation of this law to Peter Schroeder-Heister, he said that what we are doing is exactly to have structural rules instead of logical ones, right? And the thing is, I think that every time you try to do something, like put labels, or you put negation, or you put the classical context, everything is about faking at some point contraction and the right side of the sequence, and that's it. Because we need to have and that's it. So I think, yeah, so this is the ground point, and I don't think that you can get around that. So get used to that and be happy. So I mean, that's how I know either, right? There's no way. So they're trying to find different ways of talking about that without talking about instructor rules. But then,
Thank you. Thank you, everyone, as always. I have a question, perhaps a little bit more conceptual. So, I was wondering what would functional completeness look like in this case. So, a sub-question of that would be, would it be enough to have functional completeness for each of the fibers, like let's say for the inductionistic part and the classical part, or system X, system Y, for the ecumenical system to be functionally complete, or would it be like a further requirement?
yeah, my guess would be no. Because exactly because you can combine, you can have nestings of things where you have classical inductionistic and classical inductionistic, and then my guess would be no. So one thing is, so if I could say so, the ecumenical system is bigger than the classical, and in these inductionistic put together, if you put them together, in a separate way, you have a bigger system. But of course, from the ecumenical, if you restrict to everything classical, you collapse to classical logic, everything inductionistic, you collapse to inductionistic logic. So they're close to fragments, but when you put them together, then you have something bigger than the sum.
So then that will support the idea that the ecumenical system really has some expressive gains, right?
Yeah, I'd say so.
Questions?
So that's your coffee. No.